Welcome to lecture 4 of module 7. In this module 7, we are discussing on heat exchanger. Last 3 lectures we have discussed on various types of heat exchangers, their different parts and their functions of the various parts of the different heat exchangers. We have discussed in detail. Now, today's lecture we will discuss on effectiveness-NTU method of heat exchanger analysis. Method of heat exchanger analysis. Okay. So, this is in short we will write as epsilon NTU. This epsilon means stands for effectiveness. Now, NTU means number of transfer units. Number of transfer unit. Okay. Now, this effectiveness NTU method of analysis, that is epsilon NTU analysis, this method it is based on effectiveness of the heat exchanger in transferring a given amount of heat. Okay. Therefore, what happens is it is based on the effectiveness of the heat exchanger to transfer a particular amount of heat. So, therefore, what happens for this effectiveness method can help us to compare the performances of various types of heat exchangers for similar heat exchange. Okay. So, that means it helps us to understand the basic differences between two heat exchangers, to compare them, that how they are performing. So, in the form of the amount of heat exchange. Okay. That is very important, and this will help to identify or select the best suited type of heat exchanger. Okay. So, this finally helps us to select the best suited heat exchanger for the required application. So, depending upon the type of application we have, we can now, based on this effectiveness method, we can find out the effectiveness of the heat exchanger, and then we can compare the performances, and then we can select which type of heat exchanger is to be used for the said applications. So, this is very important in case of design purpose. So, therefore, the heat effectiveness method is also one important aspect in case of heat exchanger studies. Now, how to define this effectiveness? Okay. So, this heat exchanger effectiveness is defined as this equal to actual heat transfer by maximum possible heat transfer. Now, what is this actual heat transfer? Actual heat transfer means the amount of sensible heat being released or given, or maybe in terms of latent heat being given by the hot fluid and which is being taken up by the cold fluid. That is nothing but the actual heat transfer, what is being transferred through the heat exchanger. So, this can be, so if we draw that a parallel flow case and then the counter flow case, single pass case, considering a single pass case, okay, and this is one is parallel flow, another is counter flow case. Say if I write, okay, so this is a TH1, this is TC1, this is TH2 and this is TC2. This is the station 1 and this is the station 2, and here it can be area or length, whatever you say, heat exchanger. This is station 1, this is station 2, this is area. So, you can see it is like this. Okay. So, this it is say TH1, this is TH2, sorry. TH2, this is TC2 and TC1. What is happening is that in this case this is the parallel flow, this is counter flow. Okay. So, actual heat transfer for, if we say that for parallel flow, okay, actual heat transfer this will be m dot c mass flow rate of the cold fluid into CPC specific heat of the specific heat capacity of cold fluid, mCp CPC into the change in temperature of the cold fluid is TC2 minus TC1. So, this is the actual heat transfer, that means the heat being taken up by the cold fluid. Similarly, the same amount of heat is being lost by the hot fluid, and that will be equal to m dot h, that the mass flow rate of hot fluid, Cph, that is the heat capacity, specific heat capacity of the hot fluid, into the temperature difference of Th1 minus Th2. So, this becomes the actual heat transfer in case of parallel flow. And what is the maximum possible heat transfer? Maximum possible heat transfer would be, say, it depends upon that total amount of heat transfer is dependent on the driving force into the mass heat capacity of the material. So, mass flow rate into this. So, now of this cold and hot fluid, if one of the fluid is having flow rate m dot into Cp, we have two things in this heat transfer rate. One, we should say one m dot into Cp, this part, another part is delta T, that is the temperature gradient. So, and we have two fluids, one is hot fluid and one is cold fluid. Now, if we say for hot fluid or say cold fluid, for cold fluid, if m dot Cp is lower than, that means if m dot Cp for cold fluid, okay, is lower than m dot Cp of hot fluid, okay, then what will happen, delta T for cold fluid will be greater than delta T for hot fluid. Okay. So, this will be understandable because this is to maintain this. Therefore, the maximum possible heat transfer would be, say, suppose if the cold fluid is among these two, if which one is having minimum m dot Cp, if that is called as the minimum fluid, we will tell that as a minimum fluid. Under that situation, minimum fluid means it has got minimum m dot into Cp with respect to the other one. Okay. If that is the minimum fluid, then it will undergo maximum temperature difference. So, the maximum possible heat transfer would be any of the fluids, whether hot or cold, their heat flow rate, if into that the maximum temperature difference. The maximum temperature difference here it will be Th1 minus Tc1. So, that means in this particular case that the entry point, the temperature difference is maximum. So, TH1 minus TC1 will be the maximum temperature difference into the, so into that. So, if I say that TH1 minus TC1, that will be the delta T max, maximum temperature difference, okay, and then delta T max into m dot Cp of the minimum fluid. That is understandable. So, minimum fluid only can go maximum temperature difference, other fluid cannot go that much temperature difference, because this is to the other, then it will be avoid the law of thermodynamics. So, total heat exchange from one to the other will be remaining the same. So, therefore, so if m dot Cp is the minimum fluid, then into the delta T maximum, that will be actually the maximum possible heat transfer. Okay. Now, similarly, for a counter flow, actual heat transfer is if you see previously, that is what I have written. It is actually now for cold fluid m dot C Cpc into Tc1 minus Tc2, because the cold fluid is entering in the other side. Okay. Therefore, that changes will be there. So, it will be m dot C Cpc into Tc1 minus Tc2. Here the Tc1 is, because Tc1 is higher than Tc2, and that will be equal to m dot H Cph into Th1 minus Th2, the same thing. So, this is what is happening for counter flow, and the maximum possible heat transfer that we have seen, that if we say that q dot max is equal to, then we can say, that means we can say that q dot max, and this is equal to q dot actual for parallel flow, for counter flow. Or anti-parallel flow. Okay. So, q dot max is becoming now m dot Cp into, for the minimum fluid. Minimum fluid means the fluid which is having m dot into Cp, this product minimum, into will have the maximum temperature difference, that will be Th inlet minus Tc inlet. So, that definitely the cold fluid inlet temperature and hot fluid inlet temperature difference is the maximum temperature difference. Okay. So, therefore, now we can have, based on these combinations, if we have parallel flow, if we have counter flow, and depending on the situations, hot fluid and cold fluid minimum cases, we can have several combinations to have the expressions for effectiveness. So, if we write, say, for parallel flow or co-current flow, we have, say, effectiveness epsilon. For parallel and co-current flow, there are two cases, that hot fluid is minimum fluid. That means, that is m dot H into Cph is less than m dot C into Cpc. Okay. Then what will happen? We have epsilon hot fluid, right, parallel flow for hot fluid. It will be like this. It will be m dot H is the cold fluid, Cph into Th1 minus Th2 divided by the maximum possible heat transfer is again m dot H Cph into Th1 minus Tc1. Okay. So, this gives me, this cancels. So, Th1 minus Th2 by Th1 minus Tc1. Similarly, we can have epsilon P cold fluid, when that cold fluid is minimum fluid. So, I will write here parallel flow case and cold fluid is minimum fluid. So, we have 4 cases, that is here m dot c CPC less than m dot h CPH. Mind it that both the cases we are considering under parallel flow or co-current flow situation. So, this is becoming m dot c CPC into, and here in case of parallel flow it is TC2 minus TC1, TC2 is higher than TC1 parallel flow, okay, and here it is m dot c CPC into TH1 minus TC1, okay, and this is equal to TC2 minus TC1 by TH1 minus TC1, right. Similarly, if we have for anti-parallel flow slash counter flow or counter current flow, okay. Under this situation, I will write again the hot fluid has minimum fluid. So, hot fluid is minimum fluid, that is m dot h CPH is less than m dot c CPC. Okay. In that case, effectiveness for anti-parallel flow and for hot fluid, and this is becoming like this m dot h CPH into again TH1 minus TH2 by m dot h CPH into TH1 minus TC2. Yes, in this case TC2 is becoming the, because the hot fluid, cold fluid is coming from the other side. So, therefore, it is becoming TH1 minus TH2 by TH1 minus TC2. Okay. And then cold fluid has minimum fluid, that is m dot c CPC is less than m dot h CPH. So, under this situation, we will write that anti-parallel flow for cold fluid, that will be equal to m dot c CPC into, now here it is TC2 is the cold lower temperature. So, TC1 minus TC2 divided by m dot c CPC into TH1 minus TC2. So, this is becoming TC1 minus TC2 by TH1 minus TC2. Okay. So, this way we can find out different in all the cases. Finally, it is nothing but, if you just see in all the 4 cases whatever we have discussed, it is nothing but the temperature difference of the minimum fluid divided by the maximum temperature difference in the heat exchanger. So, finally, we can say that effectiveness E equals to, in any of the cases we can say the temperature difference of the minimum fluid divided by maximum possible temperature difference in the heat exchanger. In the heat exchanger. So, this is an indirectly we can, so this is the another definitions of heat exchanger that we can say. Okay. Now, what we will do is we will try to find out, develop the expression for a single pass situation for effectiveness factor in case of parallel flow and counter flow. So, expression for effectiveness factor condition is we are first considering this parallel flow and we will consider the single pass situation, because multipass is more complicated. So, we are not going for that, we will just see that how single pass situation is basically derived. Okay. Now, so to do that, first we will again draw the parallel flow situation, whatever we have drawn already. So, if this is the case, okay. Now, here it is T H 1 and this is say T H 2. Okay. So, this is the parallel flow situation. Here it is the area of heat exchange. This is the station 1 and this is station 2. So, now what is happening? This is T C 1 and it is T C 2 is the outer temperature of the cold fluid, and take any differential. Already we have discussed the partly or the similar kind of situations we have discussed while we have derived sometimes back the expressions for LMTD, log mean temperature difference. That time we have made use of similar kind of diagram and similar kind of energy balances we have seen. So, this is the area which is nothing but the differential area dA in the heat exchanger. So, what happens is, if I say the differential heat exchange dq dot, and that will be equal to minus m dot h hot fluid into Cph into dTh, because this heat being released by the heat exchanger, and we can say that dTh is the final minus initial. So, that is a negative quantity. So, therefore, we have taken a minus sign over here, and that is equal to m dot C into Cpc into dTc. dTc is the Tc2 is higher than Tc1, therefore, dTc is a positive quantity, therefore, we have not taken any negative sign over here. So, therefore, from here we can write that dTh minus dTc is equal to we can say that a dq dot is a common into 1 by m dot h Cph plus there will be a minus sign over here plus 1 by m dot c Cpc. Okay. And again we know that dq dot also can be written as UA, not A. This is happening for this dq is the differential amount of heat transfer that is happening for the area dA. So, it will be U overall heat transfer coefficient into dA is the differential area into the temperature difference. So, if I say that in this region the temperature of the hot fluid is say Th, and in this region the average temperature of the cold fluid is the Tc. So, UA into it will be dA into Th minus Tc. So, this is the temperature difference. So, we have for the small differential area we will assume that it is uniform here, it is uniform Tc over here. So, therefore, we can still write then that d of Th minus Tc will be equal to U into 1 by m dot h Cph plus 1 by m dot c Cpc into dA into we have this Th minus Tc, So, therefore, we can write that d of Th minus Tc by Th minus Tc. Now, we will do the integration from station 1 to station 2, and that is equal to U of U into 1 by m dot h into Cph plus 1 by m dot c into Cpc, and then we will integrate these for 0 to area is A. So, area at this point for station 1 is equal to 0 and there is at A. So, 0 to A, that is the situation. So, the A is the total area of the heat exchanger. So, under this situation we can say that ln Th2 minus Tc2 by Th1 minus Tc1 equals to minus U into A. We will assume that certain aspects here, that in the heat exchanger the specific heat capacities they are not changing with time, and overall heat transfer coefficients are not changing with time. So, these are the assumptions, inherent assumptions that we have taken while doing this derivation. Okay. And then this is equal to 1 by m dot h Cph plus 1 by m dot c Cpc. Okay. Now, we can write that TH2 minus TC2 by TH1 minus TC1 equals to exponential minus UA by m dot C CPC into 1 plus m dot C CPC by m dot H CPH, correct. Now, we know that for if we take assume cold fluid as the minimum fluid, okay, then under that situation C m dot C CPC is less than m dot H CPH. Now, what we will write now is that m dot C CPC as say capital CC and m dot, and in this case this is the C minimum fluid, and m dot H CPH is equal to CH capital CH, and this is the heat capacity, okay. That is, it is not specific heat capacity, it is the heat capacity of the fluid, and this is specific heat capacity per unit amount, it is not per unit amount, and this is C, we can say that C max. So, if one is minimum, then the other one is C maximum. So, therefore, we can another thing we can write over here is that m dot C CPC by m dot H CPH is equal to C min equal to CC by CH equal to C min by C max. In the present case, we have assumed that cold fluid as the minimum, and this will write as CR is the ratio. So, this is the heat capacity ratio. Okay. Now, also we can, from the energy balance we have seen that we can write that m dot H CPH into TH2 minus TH1, okay, will be equal to m dot C CPC TC1 minus TC2, okay. So, actually it should be TH1 minus this, and this will be TC2 minus TC1 and then negative sign. So, we can write like this way also. So, just one negative sign multiplication, if you see this, yeah, TH1 minus TH2, TC1 minus TH1 minus TH2, TC2 minus TC1. So, TH2 minus TH1 and TC1 minus TC2, just the reverse of that by just putting a, if we multiply with a negative sign, then we will finally get that. And then from there we can write that TH2 is equal to TH1 plus m dot C CPC by m dot H CPH into TC1 minus TC2, and then we can write that TH2 minus TC2, which is the need, because for we will see that this is equal to TH1 plus m dot C CPC by m dot H CPH into TC1 minus TC2, then minus TC2 again. So, and we know that TH2 minus TC2 by TH1 minus TC1 equals to, if we just break it like this, that TH1 will put it here plus m dot C CPC by m dot H CPH into TC1 minus TC2 minus TC2 divided by TH1 minus TC1. Then what we will get is left hand side, so TH2 minus TC2 by TH1 minus TC1 is equal to, we will just rewrite, revise the thing, rearrange basically this plus TC1 minus TC2 plus m dot c Cpc by m dot h Cph into Tc1 minus Tc2 and divided by we have Th1 minus Tc1, and this is equal to, we can write now 1 plus Tc1 minus Tc2 by Th1 minus Tc1 into, we have 1 plus m dot c Cpc by m dot h Cph. Okay. Now, if we say that cold fluid as minimum fluid, then effectiveness, already we have seen that for parallel flow and cold fluid as the minimum fluid, we have Tc1 minus Tc2 by Th1 minus Tc1, that already we have seen. Yes, Th1 Tc2 minus Tc1 by Th1 minus Tc1. So, we will have a negative sign over here, because of that reason it is Tc2 minus this will be minus of that. So, therefore, we can write, say this is equal to, so we can write that this will be Th2 minus Tc2 by Th1 minus Tc1 equals to 1 minus epsilon into 1 plus Cr. Cr is the ratio, heat capacity ratios, okay, and if this is the effectiveness, and this is equal to, in the right hand side of that expression had been exponential minus UA by Cc into 1 plus Cr. That is what was this case. Now, if we rewrite it again, then we will get epsilon equals to 1 minus exponential minus UA by Cc, okay, heat capacity of the cold fluid, into 1 plus Cr, heat capacity ratio of the minimum to the maximum fluid, divided by 1 plus Cr. Now, this UA by Cc is called number of transfer unit. So, it gives us that UA. So, it gives us the UA gives the amount of heat transferred per unit temperature difference. So, when unit temperature difference is there, then how much amount of the heat is transferred, that is given by UA. So, it is related to that heat exchanger size, and Cc is the flow rate. So, UA by this UA by Cc says how much amount of heat is being transferred by the heat exchanger per unit flow rate of the heat per unit capacity of the cold fluid, minimum fluid, and per unit temperature difference. Therefore, it is an indicative of the heat size of the heat exchanger. So, it is indicative, this is also NTU, indicative of heat exchanger size. Okay. So, then what we can write, epsilon is equal to 1 minus exponential minus NTU into 1 plus Cr divided by 1 plus Cr. So, this becomes the expression for parallel flow situation and cold fluid as the minimum fluid. Exactly in a similar way, if hot fluid as the minimum fluid, then our expression will become, this will be Cr, Cr will be C minimum by C optimum, and but NT will be UA by Ch, in place of Cc that will be Ch. So, one can try upon and try and find out that. Now, if Cr tends to 0, then what happens? Epsilon is equal to epsilon is, if Cr tends to 0, then epsilon equals to 1 minus e to the power minus NTU. So, it is then exponential, e to the minus NTU is the exponential decay, then 1 minus e to the power NTU, that is called, this is the situation happens particularly in boiling and condensation. This is we can get during boiling and condensation heat exchange, heat transfer, heat exchange. heat exchanger, because in that case that change the process fluid remains almost a constant. In this case, the process fluid remains almost constant, it does not change much. Okay. So, therefore, in that this kind of situation can happen. And another case, if CR equals to 1, then what will happen? Then effectiveness can be written as if CR equals to 1, this is 1. So, it has nothing to do much on this. So, it will be 1 minus exponential 2 NTU by 2. It is like that, 1 minus exponential CR equals to 1. So, 2 NTU by this. So, CR equals to 1 means is the case when both the fluid having heat capacity same. Okay. Now, similar derivations we can see for, but the things will be little bit different, that we can see for counter current heat exchanger. So, for counter current heat exchanger or for counter flow case, okay. Now, again let us draw this. So, depending upon the situation, I am sorry. So, if I say that this is TH1, this is TH2, and this is TC2, and this is TC1. Okay, this is station 1, station 2, and here is the area. So, under this situation, again if we write exactly similar way, the single pass case, the dq differential change in heat transfer will be equal to m dot minus h, as previously we have done, Cph into dTh, okay, and that will be equal to here again minus. Okay. The reason is m dot C Cpc into dTc. The reason is we can see that final minus initial dTc is negative. So, to make it a positive quantity, and then this is equal to again u into dA into again for a differential area, as we have done for this case, it is a dA differential area, and here it is TH, and this case it is TC. Okay, this is TH. So, then we can get TH minus TC, and like this way now we can write that d TH minus TC by TH minus TC, as we have done previously in the similar way. If we try to do over here, we will get it as minus u into 1 by m dot h Cph minus, it will be minus here m dot C Cpc into dA, and this integration will be 0 to a, and this is station 1 to station 2. Okay. So, then we will get an expression ln Th2 minus Tc2 by Th1 minus Tc1, okay, and that will be equal to minus u into a. Okay. Then we will have 1 by m dot h Cph minus 1 by m dot c Cpc, this. So, then we can write that Th2 minus Tc2 by Th1 minus Tc1 equals to exponential, and if we just take this one this side and the negative side. So, if we multiply by this negative sign over here, then we will get UA by m dot c Cpc, okay, and then we will write 1 minus m dot c Cpc by m dot h Cph. Why we are doing like this? Because again we will try to see the case for m dot c Cpc or the cold fluid as the minimum fluid. Okay. Then, so for cold fluid, being the minimum fluid okay. For cold fluid being the minimum fluid, what we will have is that effectiveness factor will be equal to TH2 minus again effectiveness factor is this, already we have seen, that is equal to for cold fluid as the minimum fluid, effectiveness factor is Tc2 minus Tc1 by Th1 minus Tc1. Tc2 minus Tc1 by Th1 minus Tc1. This is the temperature difference of the cold fluid, and this is the temperature difference for the hot fluid, maximum temperature difference. Okay. Now, here it will be, because it is a counter current flow, so this will not be Tc2 minus Tc1, it will be Tc2 minus Tc1, because we can see there Tc2 is greater than Tc2 is smaller than Tc1, so it should be, I am sorry, it should be Tc 1 minus Tc2 by Th1 minus Th2 this. But our expression had come from the integration, if we see that it is Th2 minus Tc2 by Th1 minus Tc1, this we have to expand. So, Th2 minus Tc2 by Th1 minus Tc1, we will write it as Th1 because we can see here again from energy balance as we have done previously from similar thing, that m dot h Cph into H2 minus H1 will be equal to m dot c Cpc into Tc1 minus Tc2. Here Tc1 is greater than Tc2, therefore, so we will have H2 Th2 T. So, Th2 equals to Th1 plus m dot c Cpc by m dot h Cph into Tc1 minus Tc2. Okay. So, we can write it as this is Th1 minus Cr into Tc1 minus Tc2. This is m dot h. So, this is Th2, because we are writing now, this will be here there is a minor corrections that we should make. This will be m dot into Th1 minus Th2. So, if I do this, then this will be Th1. So, if I write now, this will be negative, ulta karenge to this will be negative minus of this. So, yeah, minus here into this. Now, if we put it over here, so then we can get, this can be broken and written like this. This will be equal to Th1, this one, minus Cr into Tc1 minus Tc2 minus Tc2 divided by Th1 minus Tc1. So, this can be written as Th1 minus Tc1, just adding a subtracting with the Tc1, and then we will do that, minus Cr into Tc1 minus Tc2, then we will have plus, we have subtracted 1. So, we are adding 1, Tc1 minus Tc2 divided by simple calculations Tc and rearrangements this. Then we can write it as so Th2 minus Tc2 by Th1 minus Tc1, I can write as 1 minus Tc1 minus Tc2 by Th1 minus Tc1 into CR minus 1. Okay. And then just we have to do some arrangements. If we write, so this is, if I write it as 1 minus say k into 1 minus CR, for example, for the time being, if we write it as k, then we can write as 1 minus, so this is becoming 1 plus k, so 1 plus k into, I will write as, so if I write this 1 minus then it will become plus. So 1 plus k into 1 minus CR, and that is equal to, if I see the other derivation from the derivations here, this one we will put over there, exponential NTU into 1 minus CR. Now again we know that epsilon is equal to TC1 minus TC2 by TH1 minus TC2, and simply we can say 1 by epsilon is equal to TH1 minus TC2 by TC1 minus TC2, and that can be rearranged to give as TH1 minus TC1 plus TC1 minus TC2 by TC1 minus TC2, and that is equal to 1 by k plus 1. Okay. So, from there we can write that k equals to epsilon by 1 minus epsilon. So, just putting the value of k over here, we can write that epsilon is equal to minus 1 plus exponential NTU into 1 minus CR divided by 1 minus CR plus exponential NTU into 1 minus CR minus 1. So, this way we can finally write this 1 cancels, also we can write that 1 minus exponential minus NTU minus 1 NTU into 1 minus CR by 1 minus CR exponential minus NTU into 1 minus CR. So, this is becoming the expression for anti-parallel flow or counter current flow. Now, if CR tends to 0, then again here it will be epsilon will be equal to 1 minus, it will be 1 minus NTU, and if CR equals to 1, then this becomes NTU by 1 plus NTU. So, there are various like this. So, this is for counter current flow and single pass case. So, like that there are various expressions are available of effectiveness factor for different other passes and different various geometries, whether it is a counter current or cross flow or parallel flow or that number of passes, it can be 1, 2, 1, 4 like that. For various situations, various expressions for effectiveness factor is available in the literature and in the different places, different books, things are available. So, that can be seen and that can be tried upon even to find out the expressions, to derive the expressions, one can always try. Okay. This is just to have an idea that how to get an expression for effectiveness factor. Now, we will take up a small problem. The problem says oil of specific heat 2000 joule per kg per Kelvin entering at 60 degree centigrade and 0.3 kg per second is to be cooled to 30 degree centigrade by cold water in a parallel flow heat exchanger. Okay. Entry and leaving or exit, it is better to write exit, and exit temperatures of water are 15 degree centigrade and 25 degree centigrade respectively. Okay. Water specific heat is equal to 4200 joule per kg per Kelvin, and heat transfer overall heat transfer coefficient is equal to U equals to 300 meter square watt per meter square per Kelvin. So, calculate the NTU, effectiveness factor and area of heat exchange. Okay. So, now solution. So, from the solution we know that if you try to see Cc is equal to m dot C, Cpc is equal to 0.43 m dot C Cpc, for we have to find out, calculate the value of m dot C, that can be found out from energy balance m dot C Cpc into delta Tc is equal to m dot H Cph into delta Th. So, m dot C is equal to m dot H is equal to 0.3 into 2000 into delta C is equal to 30, because it is 60 to 30. So, 30 divided by m dot C, I have to calculate Cpc is equal to 4200 and delta C is equal to 10. So, this is equal to 0.43 kg per second. So, once we know m dot C, then Cpc is equal to, we can calculate m dot. So, this is equal to 0.43 kg into this is 1806 joule per Kelvin, and Ch, heat capacity of the hot fluid, is equal to m dot H Cph, and that is becoming 600 joule per kg Kelvin. So, Ch is less than Cc. So, Ch is C minimum, is the minimum fluid. Okay. And therefore, Cr is equal to Ch by Cc. Here, though we have done the calculations, evaluations based on minimum fluid for cold fluid, here hot fluid is becoming minimum. So, we are changing this. Now, Cr is equal to Ch by Cc, and it is becoming 600 by 1806, and that is becoming 0.33. So, once we know Cr, then effectiveness, hot fluid as the minimum fluid, we will get at Th1 minus Th2 by Th1 minus Tc1, and this is becoming 30 by 45, and this is becoming 0.67. So, we know the effectiveness factor, and then we have to find out that then we know effectiveness factor, this is equal to 1 for parallel flow exponential minus NTU, just we have seen this expression 1 plus Cr divided by 1 plus Cr here, and this is now 0.67 we got into 1 plus here is equal to 1.33 will be equal to 1 minus exponential minus NTU into 1.33. So, from here we can find out NTU is equal to 1.67. So, this is the number of transfer unit, and that is equal to, we know that UA by C mean, and then we can find out UA is equal to 1.67 into C mean is the hot fluid case into 600. So, this is becoming 1002 joule per Kelvin, and then area of heat exchange is equal to 1002 divided by the overall heat transfer coefficient is given as 300 meter square. So, this is becoming 3.34 meter square. So, this is the area of this sector. So, thus we have seen that how to use the expression of effectiveness factor, and we will give some exercises later on to see that how to make use of this effectiveness factor relationship for comparing various heat exchangers. So, this is all about today. Next lecture we will try to discuss on design issues of heat exchangers. Thank you.